So let's continue with concentration cell. We've already begun this in previous class. So what was the concentration cell? The one in which we have same metal as cathode as well as anode. And depending upon whose concentration is changed, whether we change the concentration of the electrode or the electrolyte, we have two different types of concentration cells, which will be electrode concentration cell and a second one is electrolyte concentration cell. And we saw an example where we had zinc as the anode as well as cathode, and the main thing which we discussed was E0 cell would be 0 for a concentration cell. What was the reason? The formula for E0 cell is E0 cathode minus E0 anode. And I told that E0 value is actually constant for a particular metal. When we use the same metal as anode and cathode, we get the same value for E0 cathode and E0 anode, which means E0 cell value will be 0. But this doesn't mean that E cell value should be 0, because E cell value, as I told, will be dependent upon the concentration of the electrolyte and electrode. In concentration cell, since we change any one of this, definitely the E cell value will be changing accordingly. So let's note down the two types of concentration cells. So concentration cells can be either electrode concentration cell, or it can be electrolyte concentration cell. So in an electrode concentration cell, what varies? The concentration of electrode varies, obviously, which means concentration of electrode in one beaker will be different from the concentration of electrode in the other beaker. And in second case, the electrolyte concentration will vary. Okay. Now let's discuss each of these in detail. Since an easy one, let's discuss electrolyte concentration first. Okay. As an example for this, let's take the same zinc concentration cell, this one exactly. Now the change we have to introduce here is, this is an electrolyte concentration cell, so we have to change the concentration of the electrolyte here. Okay, both will be zinc sulfate itself, but one has to be having a different concentration than the other. For example, if I put this one as 1 molar, this is my anode. If my anode contains a zinc sulfate solution of the concentration 1 molar, in that case my cathode can contain the same solution in any concentration other than 1 molar. So for example, I can take 2 molar solution and I'll represent them as, let's say we call them C1 and C2 respectively. Now I need to write the cell reaction for both, which means for anode and cathode. Okay, so the cell reaction, what is happening at anode? So usually write the anode reaction and sum it up with the cathode reaction to get the overall cell reaction. So at anode we have to undergo oxidation. So zinc should be oxidized into Zn2 plus and go into the solution. So zinc will oxidize into Zn2 plus an electron. But here we have to maintain the concentration also. So for that I'll just write here 1 molar. Plus what? Plus 2 electrons. Okay, cathode, just the opposite reaction, reduction should happen. So Zn2 plus, again mentioning the concentration, I have to write 2 molar concentration plus 2 electrons, they accept 2 electrons to become Zn. Okay, so what will be the overall cell reaction? Here I have 2 electrons cut. Zn is also common. Can I cut Zn 2 plus on the left hand side and right hand side? The answer is no, because one is in 1 molar concentration and the other one is in 2 molar concentration. So I just cannot simply cancel them. So the final or the overall equation will be Zn2 plus from 2 molar solution to Zn2 plus in 1 molar solution. This is the overall cell reaction. The next thing we are going to see is the cell potential or the E cell value. So for finding the E cell value, what is the equation which we usually use? E cell, that is the Nernst equation. E cell is equal to E0 cell minus 0.0591 by N log Q. Okay, so it's not in equilibrium, so we have to use log Q. But we also know that Q is equal to concentration of product divided by concentration of reactants, right? So in this case, if you want to find E cell, we know since it is a concentration cell, the E0 cell value is 0. So 0 minus 0.0591 divided by, what is the N value here? N is number of electrons involved, which is 2, divided by 2 log concentration of product by reactant. So what is the product here? When you look at this particular equation, the concentration of product means it is 1 molar, right? 1 molar product and 2 molar reactant. So product by reactant will be 1 divided by 2. So my answer is minus 0.0591 by 2 log half. But you also know that I can write minus log 1 by 2 as log 2. You know the reason? Just in case you don't know, this number here which you see is actually the power of the term inside. So I can take minus log half as log half raised to minus 1, which will be log 2. This is how it is. Okay, this is a common mathematics you might be knowing already. I just said it for those who have any confusion there. So instead of minus log half, I'll put log 2. So it will be 0.0591 divided by 2 into log 2. To find the exact answer, you can just calculate this one. So here what we are going to find is, in general, for any concentration cell, which means for any electrolyte concentration cell, what is the general equation for E cell, or how can we modify the Nernst equation? So here we can see that Q is product by reactant concentration. So in general terms, I just used here an example of 1 molar and 2 molar. General case, I'll write it as C1 and C2. So using that, let's try to write an equation. So I'll have E cell is equal to minus 0.0591 divided by 2. The minus came because I'm not using this equation, I'm using the very first equation. Okay. So log of product concentration is C2. Product concentration is, the product is 1 molar concentration, which is C1. So product is C1 and reactant is 2 molar concentration, that is C2. Okay, so it will be C1 by C2. So let's write C1 by C2 here. C1 divided by C2. Okay. We also know that for a cell to be feasible, their E cell value should be always positive. Only that case we can say it is spontaneous, right? So if this value should be positive, you can see there is a negative here. If you want to cancel this negative, we have to take the reciprocal of this log value. Just we have done this way, right? So if you want to take a reciprocal and still get an overall positive value, it means C2 should definitely be greater than C1, right? Or in this case, we can just rewrite this one. This can be E cell is 0.0591 divided by 2 log, taking reciprocal because I'm going to cancel the negative, C2 by C1. If this value should be a positive value, that means my C2 should be greater than C1, because if C1 is greater, the this value is going to be a decimal one, right? Means less than 0. It is going to be less than 0 if C1 is greater, and log of any value less than 0 will be negative. Hope you know all those basic things. So we know log of 1 is 0. Log of any value greater than 1 will be a positive number. Say like 2 will be positive number. Log of 0 is not defined. And log of any number less than 1, say like 0.5, will be a negative value. This thing you have to definitely know. Which means if C2 by C1 should be a positive value, C2 should definitely be greater than, if log C2 by C1 should be a positive value, C2 should be greater than C1. So in this case, for your cell to be functioning and the reaction to be feasible, the concentration of the C2, which means the concentration of cathode, should be greater than concentration of anode. That's a must in this reaction. So we'll write the special case also. Not special case, the condition C2 should definitely be greater than C1 for the cell to be feasible. Okay. This is it about electrolyte concentration cell. Now in the exactly same way we have to study the electrode concentration cell also. Well, let's look at the second one, which is electrode concentration cell. Just the opposite of electrolyte concentration cell. In this case, we will be having the same concentration of electrolyte in the anode and cathode, but the concentration of electrodes will be different, just as the name suggests. And one important thing regarding this is, we cannot usually consider the metal electrodes in this case. For example, if you consider a zinc electrode, it is obviously solid, or copper electrode, platinum electrode, all of these are actually solid. So it is almost difficult to change the concentration of solids, right? So in case of electrode concentration cell, we usually use gases. For example, hydrogen gas or chlorine gas. And we know if the concentration of solution is represented in terms of concentration itself, the concentration of gas is represented in terms of pressure. So for electrode concentration cell, we actually change the pressure of the gas at anode and cathode, and so we will be getting a feasible cell. Let's draw the representation. It is very similar to the above, but we will change the electrodes into gas electrodes. This will be platinum wire. Here we will be pumping hydrogen gas, given that it is a hydrogen electrode, and this will be obviously an electrolyte solution containing H plus ions. For example, we can take HCl. Same way, here also we will be taking HCl only. If this is 1 molar concentration, then obviously this should be 1 molar concentration, because the concentration of electrolytes should be same. And again, platinum wire and hydrogen gas. But if the hydrogen gas on the anode side, I am taking it to be, say, like 1 atm. Then on the cathode side, it can be any pressure other than 1 atm. I'll be taking like 2 atm. So just for generalization, I'll consider this as P1 atm and P2 atm. And what will we do for electrolyte cell? After drawing the diagram, we found the cell reaction, anode, cathode, and overall cell reaction, and then the cell potential. So for this also, let's find what's the cell reaction, or what's actually happening in the cell. So in case of anode, we have to oxidize the hydrogen gas into H plus. So let's take half H2, because we need only one hydrogen atom, being oxidized into H plus an electron. In this case, we have to mention the pressure of the hydrogen gas. Okay, we need to mention pressure of the hydrogen gas. So that is P1 atm. Okay, and then H plus 1 electron. In cathode, what's happening? Just the opposite reaction. H plus combines with electron, getting reduced into H2, half H2, but the pressure is P2 atm. just writing P1 and P2. Now we can easily write the overall reaction. You see two electrons will cut to H plus, they are of same concentration, so we can cancel them also. What's left is half H21 at P1 pressure, half H2 at P1 pressure, giving half H2 at P2 pressure. Okay, this is the overall cell reaction. Now we need to find the cell potential for this. Again, using Nernst equation, we have E cell, E0 cell minus 0.0591, it goes on, but we know E0 cell is 0. So let's write just minus 0.0591 divided by n. What is the n value here? It has to be 1. So just write n log q. This is the main equation. Now let's substitute 0.0591 divided by 1 log concentration of product by reactant. What is the product here? H2 at P2 pressure is the product, and H2 at P1 product is the P1 ATM is the reactant. So this will be P2 divided by P1. Now just as you did in case of electrolyte concentration cell, we have to find which should be greater, whether P1 or P2. Which should be greater? This will be E cell is equal to minus 0.0591 log P2 by P1. If I want to cancel out the negative sign, in that case definitely P1 should be greater than P2. Only then this will become, P2 by P1 will become a value less than 1. So log of that number which is less than 1 will be negative. Negative into negative becomes positive. Hence E cell value becomes positive and the cell will be feasible. So for a feasible cell, you need P1 greater than P2 for feasible cell. Okay. There is some slight addition here. Because our hydrogen was in has the stoichiometric coefficient of half, pressure terms should be raised to that power, right? While writing Q, we know that Q is equal to, for a reaction say like AA giving BB, Q will be concentration of product raised to stoichiometric power divided by concentration of reactant raised to stoichiometric power. Here the stoichiometry is half, so we have to put a half for P2 and P1. This raised to half and also this raised to half. If we consider 2 electrons being involved, that means instead of half H2 you take H2 giving 2H plus plus 2 electrons. In that case you will not have this power here, instead you will have a by 2 here. Okay, here it is only by 1 because number of electrons is 1. Anyway, we find that P1 should be greater than P2. P1 is the pressure of anode, P2 is the pressure of cathode. So we find that pressure of anode should be greater than pressure of cathode. Okay, that's what we get the conclusion. In case of electrode concentration cell, pressure of anode should be greater than pressure of cathode. What was it in case of electrolyte concentration cell? There we saw it is C2 greater than C1, and C2 was for cathode and C1 was for anode. So concentration of cathode greater than concentration of anode. Concentration of cathode must be greater than concentration of anode. Okay. Remember, they are just the opposite in both cases. Here cathode should be greater, here anode should be greater. Okay. Now we can just write for 2 electron case of hydrogen atom, hydrogen electrode again. So it's all the same, but let's simply change the cell reactions. This was case 1. Let's write for case 2, where we consider things like same cell reaction, how it will be. In case of anode, oxidation, H2 being oxidized into 2H plus 2 electrons. You need to mention the pressure, that is P1. And for cathode, 2H plus accepting 2 electron becoming H2 at pressure P2. So the overall cell reaction, we can cancel out 2 electrons, 2H plus. What is left? Again H2 at P1 giving H2 at P2. Is it any different from the above? No. Above reaction also we had from P1 to P2. So it's exactly the same without a stoichiometric coefficient. Now the cell potential value. We'll use Nernst equation. E cell is E0 cell minus 0.0591 by N log Q. I'm writing this equation again and again so that it is very familiar for you. You don't just make mistakes in this simple equation. Okay. So you have E cell is minus 0.0591. Number of electrons involved in here is 2 electrons. So by 2 into log concentration of product by reactant. Product is P2, reactant is product is at P2 pressure, reactant is at P1 pressure, and stoichiometric coefficient is 1, so whole raised to 1. We don't mention that. So in case of 2 electron involvement, we will write the cell potential like this. Okay, it's just the same. You can see how it is. Only difference is in stoichiometric power and the denominator n. Okay. So the next topic we are going to see is a little bit of physics touch, and I need you to recall what you have studied for physics. Okay, so what is resistance? All these comes under electricity or electronics part, but since we are studying electrochemistry, this is relevant here also. So you know, resistance, simply if you're going to define it, it's a property of a substance by which it will resist the flow of current through a circuit. It is the property of a substance to resist the flow of current. So a very closely related term that we study along with resistance is resistivity. What is the difference between resistance and resistivity? Resistivity is also resistance, but under specific condition, that is per unit length and per unit area. So resistivity is resistance per unit length per unit area, which in effect means per unit volume. Area into length, you get the volume. So in effect, resistance per unit volume is called as resistivity. Now you obviously know the equation which connects them. Resistance R is equal to resistivity rho into L divided by A. This is the equation connecting resistance and resistivity. When both your L and A, which is length and area, is unit, or which is equal to 1, in that case you get R equal to rho, which means that is the resistivity is the resistance when L and A equal to 1. That's a simple case. Now what we have of importance in this part is we are going to learn about just the reciprocal of resistance and the reciprocal of resistivity. So firstly we are going to study G or conductance. by the way in which the terms, when the words end, resistance, conductance, it obviously means that conductance is the reciprocal of resistance. So resistance you represent by R, resistivity by rho, conductance by G. So the definition or the proper definition for conductance will be simply, if resistance is the property of substance to resist the flow of current, conductance means it is the ability to allow the flow of current. So when you define conductance, it is the ability of a substance to allow the flow of current. And as I told, this is the reciprocal of R. So G can be written as 1 by R. Okay. So the next thing is the reciprocal of resistivity, and that should be called conductivity. And the letter which we use to represent conductivity is, it looks like K, but it is actually called as kappa. So conductivity is represented by kappa and conductance by the letter G. So kappa, as I told, this is the reciprocal of resistivity. So you can write it as kappa is equal to 1 divided by rho. Okay, now if you want to write this in terms of R, how do you write? This in terms of R means, rho is equal to, we know R is equal to rho L by A. So rho will be equal to R A by L, right? Rho will be equal to R A by L, or you can write 1 by rho will be equal to 1 by R into L by A. So we're just rearranging this equation. I can write, if I take rho to this side and R to this side, I'll have 1 by rho is equal to 1 by R into L by A. Hope this is okay for everyone. 1 by rho will be 1 by R into L by A. So here we have 1 by rho. So I can replace this as 1 by R into L by A. 1 by R into L by A. But I already know what is 1 by R, right? 1 by R is called G, conductance. And what is L by A? L by A is actually a constant value for a particular cell, and so we actually call it as cell constant. L by A is called as the cell constant value. This is cell constant. And how do we represent cell constant? By the letter G star. So L by A can be written as G star. So I can write kappa is equal to G into G star, which means conductivity is product of conductance and cell constant. Conductivity kappa is product of conductance G and cell constant G star. Now we have learned conductivity. The next thing which is closely related is molar conductivity. And it is an important topic, molar conductivity. Just by the name you can say what is the definition for this. Molar conductivity means it is the conductivity of electrolyte per mole, or the conductance produced from 1 mole of electrolyte of the ions. So it is the conductance, molar conductivity as well as molar conductance. Both can be used interchangeably. Both are actually quite similar. Okay. And how do we represent this one? It is always represented as lambda m. Writing this m is important because there is another conductivity which we say equivalent conductivity, which will be represented as lambda equivalence, lambda eq. So lambda m means molar conductance or molar conductivity. And the definition is it is the conductance of ions produced from 1 mole of electrolyte. Dissolved in V volume of solution. Okay, so let's see how the equation looks like. So molar conductivity lambda m is product of conductivity kappa into molar volume. And what is molar volume? Molar volume means volume per mole, but that is actually V divided by N. So total volume divided by total number of moles will give you molar volume Vm. But we also know that number of moles per volume is called as concentration C. So V, since N by V is C, V by N should be equal to the reciprocal of C, that is 1 by C. So instead of Vm, I can write it as 1 by C. So lambda m has another equation which will be kappa into 1 by C or kappa divided by C, the concentration. So this will be the equation that you will be using more often. Molar conductivity or molar conductance is equal to conductivity divided by concentration. And this is a bit tricky equation because only for SI units you can actually use this equation. When the unit changes, you obviously have to do certain changes to this equation that we are usually doing in many of the problems. But here there's a simple trick, that is, in most questions, firstly I'll tell regarding this equation. The unit for lambda m is actually Siemens meter square mole inverse. You hope you know what is Siemens if you have not mentioned it before, but we know that for resistance the unit is ohm. For resistivity you can find accordingly from the equation. For conductance it will be ohm inverse, or you can call it as Siemens S. This is Siemens, and that Siemens is what we are writing here as S, Siemens meter square mole inverse. This is the unit for lambda m. And for kappa it is going to be Siemens meter inverse. And for concentration in SI unit it will be mole per meter cube. Okay. You do not write mole per liter because liter is actually dm cube and dm is not SI unit. So in this case concentration is in mole meter raised to minus 3. If any of these values change, as I told, you will have to convert it into this unit and only then you can apply this equation. But in most questions, kappa will be given in Siemens centimeter square mole inverse. Lambda m will be given in Siemens centimeter square mole inverse. Kappa will be given in Siemens centimeter inverse, and concentration will be given in mole per liter. Obviously any one of these values will be missing and you will have to find it, but the usual trend which we find is instead of meter they will put centimeter, and instead of meter cube, that means for concentration, they will put liter. So accordingly, if this is the trend that you see, there is one short equation which we can use instead of doing the entire unit conversion. You can try that and see, but eventually you will reach into this equation, that will be lambda m is equal to kappa into 1000 divided by C. Just we are multiplying the above equation by 1000, and this will take care of the three changes that you have brought into unit. Those are lambda m changed into Siemens centimeter square mole inverse, kappa changed into Siemens centimeter inverse, and C has changed into mole per dm cube, or you can call it as mole per liter. Okay, so if this is the combination of units that you get, then you can use the second equation. So that is about molar conductivity. One important question to think about in here is, what happens to conductivity and molar conductivity on dilution? So dilution means we are actually decreasing the concentration of that particular solution. What happens to conductivity and molar conductivity during dilution? You have to note this. On dilution, what happens? The number of moles in the entire beaker, if you imagine, just because I'm diluting, there will be no change in number of moles, in total number of moles. So initially my solution was up to here, okay, and then I diluted it. Now it has become till here, but this does not change my total number of moles. So total number of moles unchanged. But what happens to the number of moles per unit volume? If initially my volume was up to here and I had it this way, total number of moles were concentrated into small volume. But now my volume increased, say up to here, then total number of moles will remain same. But what happens? Number of molecules or number of moles per unit volume will decrease. Initially I had so much number of moles per unit volume, but in second case, when I increase the volume, the number of moles per unit volume in one unit volume will decrease. So total number of moles unchanged, but number of moles per unit volume will definitely decrease on dilution. So what happens to specific conductivity? Since it is dependent on the number of moles per unit volume, specific conductivity will definitely decrease on dilution. But what about molar conductivity? We might think that since the number of ions in particular 1 mole has actually decreased, or per volume has decreased, so this should also decrease. But if you just think about it, molar conductivity means it's the conductivity of 1 mole of ions, right? So initially the 1 mole of ions was concentrated in a small region, but on dilution the same 1 mole of ions now taking up large volume, right? So initially if I want 1 mole, I have to take only this much part, but now after dilution, if I want to get 1 mole, I have to take some big part. Large volume should be considered to get 1 mole itself because of dilution. Because during dilution, the whichever solvent you're using is going to take up some space. The 1 mole of the electrolyte is actually being scattered. Now you have to consider a large volume to get that 1 mole. So what happens to the ions? Since you're considering large volume, your ions have now more space to travel. More space to travel means their mobility has been increased. So even though the number of ions per unit volume decreases, that will not affect your lambda m value, because lambda m means it is the conductivity produced by 1 mole of ions. Now your 1 mole of ions is occupying large space, hence they have higher mobility. Higher mobility means there is high chance for conduction, and therefore lambda m value increases due to increase in mobility. I hope that's clear for you. And why does kappa decrease? Due to decrease in number of moles per unit volume. Okay. Next thing is somewhat again similar to molar conductivity. As I told, it is equivalent conductance or equivalent conductivity. Okay, equivalent conductance. And how do we represent it? Same lambda, but instead of m you put EQ. That is equivalent conductance or equivalent conductivity. Now this, as the name suggests, is the conductance of one equivalent of a substance. So equation will be similar to the above. That means we will be using lambda m is equal to kappa by C. Instead of concentration, you will be using normality. Okay. And as we usually get in these units, let's write for the second equation. So lambda equivalent is equal to kappa into 1000 divided by, instead of concentration in molarity, you will be choosing normality N. Okay. So how do we relate normality and molarity? Do you know the connection between them? Normality, which is represented as N, here N actually represents normality. Okay, please note that also. So to connect normality with molarity, we have one factor which we call as the valence factor, and the equation is normality is Z times molarity. Okay, normality is Z times molarity, and this Z is called as the valence factor. Normality is represented as N, molarity is represented as M. So one can write N is equal to Zm is equal to valence factor times M. Okay. Now what is actually the valence factor? Valence factor means the total number of positive charge or the negative charge. In any terms, you can say either in terms of positive charge or in terms of negative charge. Anyway, it is total positive or negative charge present in the solution. That is called as the valence factor. Now, if you can connect normality and molarity, you should obviously be able to connect lambda m and lambda eq. Why? Because the only difference here is in terms of C and N. Obviously C is actually molarity, because you see C is mole per liter. This means molarity M. So if you get a connection between M and N, you will definitely get a connection between lambda M and lambda EQ. Okay, so lambda M is inversely proportional to molarity. Lambda EQ is inversely proportional to normality also. So if I want to write, I'll have lambda M inversely proportional to molarity and lambda EQ inversely proportional to normality. If I take a ratio of these both equations, say like equation 1 and 2, 1 divided by 2, how will I write that? Lambda M divided by lambda EQ will be equal to 1 by M into divided by 1 by N, right? That will be written as 1 by M into N, which can be written as N by M. Hope you know how to take reciprocal. It's simple. So lambda M by lambda AQ can be written as N by M. But what is N by M from this equation? N by M will give you valence factor Z, which means lambda M by lambda EQ will give you Z. Or I can write lambda M is equal to Z times lambda EQ. Earlier I wrote N was equal to Z times molarity. So here I am writing lambda M is equal to Z times lambda equivalent. Okay, these both equations you have to remember them. A simple question on the relation between normality and molarity, just for it to be clear to you. So the question is, if I have 1 molar concentration of H2SO4, sulfuric acid, what is its normality? What is the normality of this solution? So I'm asked to find normality given molality. I know the relation connecting them, N is equal to Z times M. And what is value of molarity? It is 1. So N will be equal to Z. Whatever is the valence factor value, that will be equal to normality. How do I find valence factor? We already told the definition. It was total number of positive charge or total number of negative charge. H2SO4, if you try to split it, I'll have 2H plus SO4 2 minus. So total number of positive charge here is positive charge, total number is 2. Total number of negative charge is also 2. I have to take either one of them. I can take it as 2. So I got Z is equal to 2. Valence factor is 2. Since N is equal to Z, which means normality is also equal to 2. Then I can write 1 molar solution is equal to, of 1 molar solution of H2SO4 is equal to 2 normal solution of H2SO4. This is what I'll be able to infer from this relation. Hope that's clear. So we have seen from the concentration cell, we have seen the electrolyte concentration cell, the cell reaction, cell potential, and we saw that C2 should always be greater than C1. That means concentration of cathode should always be greater than concentration of anode. And then we saw the electrode concentration cell. Firstly, we saw it for a hydrogen electrode with 1 electron involvement and also with 2 electron involvement. Then we again studied some basic terminologies related to electricity: resistance, resistivity, conductance, conductivity, molar conductivity or molar conductance, and equivalent conductance or equivalent conductivity. One important term is cell constant G star. It is equal to L by A. Okay. And we also studied relationship between normality and molarity, also lambda M and lambda EQ.